Right, this video goes along with this lecture note packet, the electromagnetic spectrum notes. And so I'm going to start out a little bit differently, and I have drawn a spectrum. I'm going to talk a little bit about this for a minute. Okay, so at some time in your science career, you should have studied the electromagnetic spectrum, which is all types of radiation. We often refer to this as light, but I don't want you to be confused because it's not all light that we see. Okay, so technically these are all types of radiation. So in all of these types of radiation are traveling through space like a wave, and that's why I have this wave, drawn here. Okay, so traveling through space like a wave like this. So there are technically 7 types of radiation, and they are gamma rays, X-rays, ultraviolet, visible light, infrared, microwave, and radio. So you've probably heard of all types of these. Radio waves are what lets you listen to the radio in the car. Microwaves are actually the energy that's used to cook your food in a microwave. That's its name. Infrared, used for heat, kind of like heat vision. If you've ever seen the heat vision goggles or mapping tools, that's what that's for. Visible, of course, is all the light we see, and visible light can be broken into the colors of the rainbow, which are given the acronym ROY-G-BIV. It's backwards on this one only because of the way I've drawn the picture, but that stands for red, orange, yellow, green, blue, indigo, and violet. So past the visible light, we have ultraviolet, which comes from the sun. And if you have ever, read a sunscreen bottle, when you're purchasing sunscreen, it'll say protects from UVA and UVB, and those are types of ultraviolet light from the sun. So we're getting more energetic up on this end of the spectrum, much more energy involved with these types of light. Then we have X-rays. Of course, most of us have had an X-ray before, even if it's just been our teeth at the dentist's office. And if you think about it, they put that heavy apron on you to protect you from the X-rays. And then gamma rays. Gamma rays are often used in some types of cancer treatments, chemotherapy, things like that, radiation treatments. So this is the electromagnetic spectrum, and this is something that would be very helpful for you to know. And by know, I don't mean memorizing the numbers that are on this sheet. Okay, nothing like that at all. But the sequence of these, and we'll talk about a little bit in class about how we can better remember this. But I want you to notice that visible light, which is all the light we see, is just this tiny section of the spectrum. I've noticed that the red visible light backs up to infrared, and the violet section of the spectrum backs up to ultraviolet. So no matter which way your spectrum is drawn, if it happened to be flipped, you should be able to put in the colors of the rainbow. And so we'll go back to this in a few minutes. That is on your note sheet, but obviously it's not printed in color. So if you want to, you may write in, going this way, ROY-G-BIV, okay, at the bottom there. And if you want to color it, you can. Or if you want to make a spectrum that looks something like this, that might be helpful to you too. Okay, so before we can talk about how this radiation moves through space, we need to talk about parts of a wave. So all of these types of radiation are traveling through space like a wave. And so if we're going to talk about waves, we need to know the parts of a wave. So depending on what math class you're in or you've been in, you may know some of this, especially if you studied things like sine and cosine waves. All right, so the very top part of a wave right here, the peak per se, is called the crest. Okay, so that is the crest of the wave. There's a crest here, a crest here, a crest here. The height of the wave, so to speak, is referred to as the amplitude. Okay, so that's technically the height of the wave. The distance from crest to crest is referred to as the wavelength. And it is it's given the symbol lambda, okay, which is lambda. Lambda is a Greek letter, and it's kind of like a diagonal like that, and then a little swirl kind of, and that's how you draw the lambda symbol. And so the wavelength is the distance. Here, I'll get rid of that. Is the distance between the crests. Okay, so because it's a distance, it's going to be measured in units of distance. So it can be measured in units like meter, centimeter, millimeter, and in this chapter we're going to see a lot of nanometers. Okay, nanometers are very small, and while we're talking about them, the conversion factor for nanometers is that there are 1 times 10 to the 9th nanometers in a meter. So you might want to write that down on your paper somewhere, because you will be using that as a conversion factor in this chapter. Okay. The only other part of a wave that we haven't talked about is a little bit harder to understand, and that is something called the frequency. And it's not really capable of being labeled, so I will define and then I will describe frequency to you. The definition of frequency is this. It is how many wave cycles pass a given point, in a given amount of time. Okay, it's how many wave cycles, or how many, I guess that's a good enough explanation, how many wave cycles pass a given point in a given amount of time. So I'm going to draw you two, I left my eraser over here, give me 1 second. I'm going to draw you 2 waves. We'll call them wave A and wave B for convenience sake here. And, oh, I should have left that one. And then we'll talk about the frequency. So we'll put this first wave back, which looks something like this. Okay, and then here is wave B. Okay, we'll call it A and wave B. All right, so if you think about the best way to explain frequency is this. If I had a line right here, okay, and I was looking for how many, we can say crests to make this easier. If I was looking for how many crests of the wave pass this point in some amount of time, so say 20 seconds, okay, how many wave crests pass this point in 20 seconds? So first of all, the units for frequency are technically waves per time. Okay, and most often you'll see this as waves per second. Now, waves doesn't have a unit, so this gets a little bit odd, but the units for frequency are actually 1 over some unit of time. Okay, most often you will see 1 over seconds. Okay, that doesn't mean you can't see 1 over minutes, but most of the time you'll see 1 over seconds. And you should know that another way to write that is seconds to the -1 by bringing that exponent up from the denominator of that fraction. So the units of frequency are a little bit weird. They're not seconds. Okay, it's 1 over seconds, or seconds to the -1. Of course, it could be 1 over minutes or minutes to the -1. Those are also acceptable units for frequency. Okay, so back to my wave picture. If I'm looking at these 2 waves and I'm looking at which wave has more crests that pass this point in a given amount of time, and the answer is pretty obvious, and that wave would be B. Okay, B has a larger frequency. Okay, so B has a larger frequency in this case. I'm going to get rid of this. All right, so B has a larger frequency, which means A has a smaller frequency. But I want you to look at their wavelengths. Okay, if we go to compare their wavelengths, look at A's wavelength with B's wavelength. It's pretty obvious here which one has the larger wavelength, and that would be wave A. So wave A has a large wavelength, remember that's lambda, and B has a smaller wavelength. So if you notice anything about this, there's a relationship here, which is an inversely proportional. Frequency and wavelength are inversely proportional. And I forgot to tell you the variable for frequency. That's my fault. Frequency is given the variable, it's not really a variable, it's a Greek letter. It's the Greek letter nu. Okay, and it looks kind of like a cursive V, or a script V. Okay, and it's the Greek letter nu. but it looks like a V. So, takeaway is a large frequency equals a small wavelength, and vice versa, and this is an inversely proportional relationship. Okay, as wavelength increases, frequency decreases, or as wavelength decreases, frequency increases. Okay, super important point in this first section. Okay, so we know wavelength now, we know frequency, we know units of both. So now we're going to talk about the relationship between frequency, wavelength, and the speed of light. So this is kind of the second section on your notes down here. Okay, so all types of radiation moves through space at a constant speed. Okay, and that speed is the speed of light. Okay, all radiation moves through space at a constant speed, which is the speed of light. Of course, constant means it doesn't change. The speed of light is always the speed of light, which means all those types of radiation, okay, visible, gamma, infrared, radio, they all travel through space at the speed of light. The speed of light is given a variable c. Okay, why it's c, I'm not sure. And the speed of light is equal to 2.998 times 10 to the 8th meters per second. Okay, it's a speed. So meters per second is, a unit that makes perfect sense here. 2.998 times 10 to the 8th meters per second. This is a constant that's given to you on your AP cheat sheet, so to speak. It's available to you, for the test. Okay, so speed of light is a constant. There's a formula here in this section that says the speed of light, c, is equal to the wavelength of light times the frequency of light. Okay, so the wavelength measured in meters times the frequency measured in 1 over seconds, or seconds to the -1. If you think about it, this formula makes perfect sense. If you take wavelength measured in meters and multiply it by frequency measured in 1 over seconds, you end up with m over s, which is meters per second, which are the units for the speed of light. Okay, so what this formula allows you to do, think about it, speed of light's always a constant, okay, it's always given. We know speed of light all the time. So if I know the wavelength of any type of light, I can find its frequency, or if I know the frequency of any type of light, I can find its wavelength, okay, by using this very small equation. This also shows you that the inversely proportional relationship. Think about it. If the wavelength times the frequency always equals a constant number, which in this case is this, okay, the wavelength times the frequency always equals this number. If you had a type of light and you increase its frequency, what would its frequency have to do, or how would its frequency have to change? Well, if they still have to multiply together to equal a constant, then this number has to get smaller. And there it is, right there, that inversely proportional relationship between frequency and wavelength. This is a super, super important point in this section. However, all these types of waves, while they have different wavelengths and frequencies, they all travel through space at the same speed. So if we go back to our picture, our spectrum, okay, whether it's on your note paper or if you've drawn one, if you look at the wave that I drew in here, okay, we can label a couple things on our picture. And what we can now label is that this side of the spectrum has a very large wavelength, okay, large wavelength on this side, which means it would have a very small frequency. Large wavelength, small frequency, which is the reverse of this side of the spectrum. This side of the spectrum has a very small or very short wavelength, okay, but a very large frequency. So it's very important to know, because you could be asked a question like, which type of light has a a larger wavelength, microwaves or ultraviolet. And if we know, microwaves versus ultraviolet, if we know that the bigger wavelength lies on this side, then my answer, of course, is microwaves. Okay, so those are some types of questions that you could be asked. All right, if you flip in your packet, there are 3 practice problems that if you are, current with me now, I would advise you pause the video, you attempt to solve these practice problems, and I will just go ahead directly here and solve them for you. But if you are, ready to do so, just pause the video, attempt to solve these problems, and then you can come back and watch the solutions. All right, I'll try to do this quickly. The solutions to the practice problem number 1 was asking you to find frequency. So I know that this is my formula. If I'm asking to solve frequency, I'm going to divide by wavelength. My formula is frequency equals C over wavelength. Okay, the speed of light is a given. I just looked that up. My frequency in this case was 589 nanometers. Okay, you might be inclined to put that in the denominator, but you have a unit mismatch, so I need to change this. And if you jump down and change it, using the conversion factor that I just showed you earlier, that gives you a wavelength of 5.89 times 10 to the negative 7th meters. Notice now my meters will cancel, leaving me with not seconds, but 1 over seconds, which is in fact the unit for frequency. I'm looking for 3 sig figs here in my answer. I do this math and it comes out to be 5.09 times 10 to the 14th. Okay, so that's the answer to number 1, 5.09 times 10 to the 14th, 1 over seconds, or seconds to the negative 1. Okay, either would be acceptable in this case. All right, answer to number 2. Let's see, a laser used in surgery produces radiation with a wavelength of 640 nanometers. Calculate the frequency. So again, I'm asked to find frequency. Frequency equals C over lambda. This is the same type of problem. Speed of light. Okay, you're given a wavelength in nanometers. Whoops, I need to change that to meters. It becomes 6.4, technically 0 times 10 to the negative 7th meters. My meters cancel. Again, I'm left with seconds to the negative 1. And in this case, to 4 sig figs, my answer is 4.684 times 10 to the 14th, seconds to the negative 1, or 1 over seconds. And in number 3, let's see, a radio station broadcast at a frequency of 103.4 megahertz. Okay, and then here they give me a conversion factor. Calculate the wavelength. Right, in this case, wavelength equals C over frequency, 2.998 times 10 to the 8th meters per second. They're giving me this unit I haven't seen before, which is a megahertz, but it's okay because they give me a conversion factor, which says that a megahertz is, let's see, 1 megahertz is 1 times 10 to the 6th seconds to the negative 1. So it's fine because they gave me a conversion factor. So I changed that, end up here with, let's see, 1.034 times 10 to the 8th seconds to the negative 1. Plug that right into here. Notice that my seconds are going to cancel. Okay, my 1 over seconds and seconds to the negative 1 will cancel, leaving me with meters, which is a perfectly acceptable unit for wavelength. And when I do this math, it ends up being 4 sig figs, 2.899 meters. Okay, is my answer, 2.899 meters. Now I could turn that into nanometers if I wanted to, but the problem doesn't ask me for that, so I would just end my calculation there. It's perfectly acceptable to leave it like that. One thing I have not told you is that this problem talked about megahertz. Okay, hertz is actually another unit for frequency. You don't see it as often. You could see it in a textbook or a you know, AP question. And actually, it's a pretty easy situation because a hertz is just equal to a second to the -1. Okay, so it's kind of a nice conversion factor. Now, mega, of course, is a metric prefix, and that's why this conversion factor was given to you. But a hertz is just a second to the -1 power.